Yeah, so I should begin by apologizing for something, which is that you may think that I am some kind of expert on entanglement, and I'm not. Okay, I know I have worked on quantum field theory for many years. Yeah, maybe. Scalar fields, free scalar fields. So everything I know about entanglement, I learned very recently, and I'm probably missing a lot. The literature is absolutely enormous by now, so I'm coming to the party quite late. Uh, but I need, at least for this purpose, I need only a small subset. And I'll tell you the papers that I think are relevant. But there are probably a lot of things out there that I don't know about. And I have some questions that perhaps some of the actual experts can help me with. Okay, so what I'll talk about is the overlap of two ideas, relativistic causality and entanglement. And this goes back almost a century, ever since the Einstein, Podolsky, Rosen paper. There has been a lot of interest in the interplay between quantum mechanics and relativity, entanglement, and causality. But it has all come to the surface now because of many exciting experiments over the last few years, and the possibility of perhaps inventing new devices that exploit some of these amazing physical phenomena. But I don't have anything to say about that. So I'll talk about a somewhat uh, idealized situation, which may be experimentally accessible, but certainly not immediately. So the idea is that you have two detectors which measure a massless field. I'll take them to be scalar fields, but that's not really important. You could also do this for the photon. The important thing is that it is massless and it is free. Those are the two important things. And these detectors are separated by a space-like distance, meaning that they cannot communicate with each other. In fact, the distance is large compared to the size of the detectors. Now, in spite of the fact that they cannot communicate with each other, their measurements will not be statistically independent. That's because you're making a measurement on a state. I will consider the ground state. You could also consider thermal state. But to be specific, I'll talk about a ground state. Now, this state we'll assume, established long before you turned on the detectors. So, so there is no violation of causality. The state has already been formed by some time in the distant past. And now you're starting to make a measurement. This is the situation. So I was inspired to look into this by a colloquium by Natalie Clough from Duke University. And she's part of a collaboration that did the original fundamental work on this, except they did this numerically, that is on a lattice. That's where these phenomena were originally discovered. And from algebraic quantum field theory, I think everyone expects that there is entanglement in this situation. When two space-like observers, when they make a measurement on the ground state, you expect it to be entangled. But the question is, how does it actually show up and what is the actual measure of it? And I don't think that at least the algebraic quantum field theorists had an answer to that. And what they showed, there are about three papers on this. What they showed is that there is entanglement. We can measure it by a quantity called negativity. I'll explain what that is. And they showed that this negativity decreases exponentially with the distance. So people who looked for it earlier numerically did not see it because it is an exponential decay, and you have to do some high precision computation in order to actually see it. You do naively, if you do just the kind of numerical calculations that I'm able to do, you wouldn't see it because of the exponential decay. Yeah.
So the two space-like regions,
Yeah.
two regions are space-like separate.
Yes.
And the ground state, you are getting a representation on the Fox space.
Yes.
Scalar,
Yes.
right?
Yes.
Otherwise, it's
That's right. The Fox space. Yeah.
Then in quantum field theory, there are results that you can change this. You have got a global state, which is given by the vacuum.
Yeah.
By the way, that already gives entanglement because
Yes.
yes. The second theory.
Yes, exactly. Exactly. Yeah. Exactly.
Then valuation of that thing on one path can be changed arbitrarily to any other state without affecting the first.
Yes.
Concrete results.
Yes. Yes.
So
all that is true. The question is, how do you translate it into something that somebody might actually measure? Like you want to produce some kind of an experimental prediction out of this. Conceptually, you're right. We definitely expect there is entanglement. But what is the precise measure of it, and how does it depend on the distance? That's the question. Yes. Yeah. Yes. Yeah, it is possible. I just don't know about it. Yes, everyone is telling me to study relative entropy, and I have not come to that yet. And it is very possible that what I will talk about is related to that, but I don't know the connection. In fact, I would like to know more about it. Hmm? I will, for simplicity, consider the case where the observers are space-like separated. You're probably right. Time-like can also, but that'll be a little more involved. So yeah. Yeah, so I'll talk about detectors. Each one has a size d, and they're separated by a distance r. R is much greater than d. That's the situation.
So there is also this result back in 2000 or something, where they have shown that if I create a correlated state with two photons or something, and
Can you speak louder?
So if I take two particles, like two photons together, to create some correlated state, maybe maximal entanglement, and take one photon, quite far away in accelerated frame with respect to
Okay, yeah.
then this entanglement will decrease if I increase the
Yeah, it is probably related. I'll come to why it may be related to the accelerated observers, but I'll come to that, yeah. Okay, so what is the setup? To be more specific, I'll consider a massless free scalar field. This is the simplest quantum field theory, but with minor changes, I can consider a photon in free Maxwell's theory. There are two detectors. I'll think of them as spheres of diameter d, separated by a distance r, which is greater than d, in fact, much greater than d. So they don't overlap. Now, although the field has an infinite number of degrees of freedom, we'll assume that the detector is only sensitive to one mode. Each detector is sensitive to one mode. So there are a pair of functions, u and v, which define canonically conjugate pairs. This is the integral of a momentum. Yeah.
The detector is also quantum.
Detector is also quantum, yeah.
It's also quantum.
Yeah.
If you have only one mode in the detector,
Yeah.
it cannot be localized.
Okay. Why is that? Okay, maybe.
You cannot write a local.
Yeah, I'll tell you what I am going to do, and you can tell me whether it is local or not. Okay. So I'll assume that there is a function u, u1, which is 0 outside of the sphere I1. And so u1 and v1 are functions which are 0 outside of I1, and u2 and v2 are functions which are 0 outside of I2. I1 and I2 do not overlap. Moreover, the integral of u1 times v1 is 1, and the integral of u2 times v2 is 1. So there are functions of that kind we can choose. And therefore, these variables I've defined here, there are 4 variables, they form a canonically conjugate pair. They satisfy these conditions. This integral condition is so that it is 1 here and not something else. Okay, now there are, I consider the scalar field theory in n plus 1 dimensions, n space and 1 time. And I consider 2 situations, n equals 1 and n greater than 1. They behave somewhat differently because the scalar field in dimension 1 has a logarithmically varying correlation. But that's a little bit spurious because only the derivative of the scalar field for a massless scalar field is interesting. And so I have to do things slightly differently for n equals 1 and n greater than 1. So
Scalar field is massless.
Massless, yeah. Massless free, the simplest possible thing. Okay. Now the aim here is to find the best possible choice. Huh? You see, if you have a mass, an exponential decay is not surprising. So I want to, yeah. By the way, I want to emphasize that I haven't actually finished this project. It is sort of work in progress. I've reduced it to some integral equations, and they're not so easy to solve. I'll explain why. Okay, linear integral equations. So I don't still have an explanation for this exponential decay. Okay, but I have an idea why that is so, but I have not established that. Okay, the exponential decay was the main discovery. That's the thing that I want to explain.
How important is it that it be a thermal state?
Yeah.
Does it matter if you go to the T going to 0?
Yeah. I'm talking about the ground state. So it is not thermal. Temperature is 0. You could,
You wrote thermal.
no. You could also generalize it to thermal, but I'll talk about the ground state. Yeah, this is the ground state. I'm not going to do much more than the ground state.
But as you said,
Yeah.
mass,
Yeah,
exponential decay can be,
understood. Yeah.
you can take the mass going to zero.
You could, yeah. Yeah.
Such that it remains.
Yeah. You could do that. In fact, that is what they do. The numerical calculations do exactly that, but I won't do that. Okay. So, yeah.
Like the paper of talk that you mentioned
Yeah.
was done because it was a lattice kind of.
That's right. That is calculation.
Here the goal is to we just learned how to
I'm essentially going to try and reproduce this, approach it in the continuum. The reason to use the lattice is to avoid ultraviolet divergences. But a free massless scalar field, we know how to handle those ultraviolet divergences in the continuum. And that's what I'll do. And I'll use some tricks of functional analysis that subtract out all the infinities. Because it is free, you can do that. Yeah. So my aim is to find the best choice of these functions u and v that will give the most entanglement. Okay. And I will reduce this question to a variational principle. And the problem of getting the best answer can be reduced to minimizing a certain function, which you'll see. And this will give you a linear eigenvalue problem. It's an integral equation. And you will see why integral equations appear. So that much I have. The solution of this numerical, integral equation is harder than I thought, and I'll explain why that is so. But I still think it can be done. It's just that I ran out of time in working it out. Okay, I hope to go back to it. I want to continue this. Okay, so since I was completely new to this, I went back and read just enough that I can put through this program, and I'll talk about this subset of the literature that is relevant, not the whole thing. And there are probably a lot more out there that I don't know about. First of all, what is a state? I talked about a state. I'll take the algebraic quantum field theory point of view to a state, or even algebraic quantum theory point of view to a state. You have an algebra of observables. For simplicity, think of them as bounded observables. And a state is simply a linear function that associates to every observable a complex number, which is sort of its average value. And this average value, the expectation value, must be positive on positive operators, must be 1 on the identity. In other words, a state is simply a non-commutative analog of a probability measure. That's what a state is. But it turns out that to really put through the arguments that are needed, they're actually using, in the literature, something slightly weaker than a state, which I will call a proto-state. Because, I've been reading about all these theories of how states, as in countries, form. And the proto-state is something that appears there. A proto-state is a linear function where I replace this condition of positivity by the condition of reality. But it may not be positive. That's the important thing.
So this is not a state at all.
It's not a state.
It's a pre-dual. What they call pre-dual.
Yeah, that's right. Yeah, that's why it's not a state, it's a proto-state. It is not quite a state.
It's a pre-dual.
It's a weaker notion than a state. Yeah, it is something like that. Yes, exactly.
Every quadrant algebra.
Yeah. That's right.
You have to tell me, sorry about that.
Yeah.
Something about the topology of this.
Yeah, okay. So I was trying to avoid talking about the topology, but I can think of it in the natural topology is the weak topology because you're talking about expectation values. But I think I'm actually effectively using the strong topology. But that's a
You
technical
don't have
issue.
expectation values. You got simply rho,
Yeah.
which is fulfilling this property.
Yeah, it's just a linear function. You're asking in what sense is this a linear continuous function?
No, it's linear continuous.
Yeah.
Continuous requires a topology.
Yes. So I'll actually use the operator topology on the space of the soup norm on the bounded function. Yeah.
Sorry, ultra big.
Yeah. I don't want to get into that. I will.
in that equation.
Yeah.
You don't need the rho prime on the right hand side.
I meant to say rho prime. Yes. Yeah. I kept sending Rakesh updated versions of my talk where I fixed minor things like that. Yeah. I meant to write rho prime actually. Yes. That's correct. Okay. Next, there is an important inequality, which is a version of the uncertainty principle, and it is somewhat souped up version of an uncertainty principle. So suppose I have a set of observables satisfying canonical commutation relations. I have 4 of these, but you can take any. Actually, I should have written 2n there, not n, but 2n. It's always an even number. N degrees of freedom is what I mean. Now I can define a correlation matrix. By the way, obviously I can just add a multiple of the identity to these so that the expectation value of each of these is 0. There's no loss of generality there. Now I look at the correlation matrix, which is sort of the expectation value of the product. And because these don't commute, I take the average of the 2 orders and I look at that. Now this quantity, these C's are Hermitian operators. So this G is a positive operator. In other words, it is a matrix which is positive. But the important thing is that in a quantum theory, it has to satisfy a condition that is stronger than just positivity. I will show that what is positive is not just G, but G minus 1/2 Ij. J is that antisymmetric matrix with 1 and minus 1. And that proof is basically the same as it is a proof that you find in all quantum mechanics textbooks as the proof of the uncertainty principle. It's one of the proofs of the uncertainty principle. And it is simply that you start with the axiom that A dag or A has positive expectation value. You take linear combinations with complex coefficients. So this is A and this is A dagger. So this must be positive. Then you write it in terms of commutators and anti-commutators, and that gives you this inequality. This is going to be very important. This inequality.
You're using the fact that it is a state.
Yes. This rho is a state. So exactly. That's right. Later on, I will need a proto-state, but now it is actually a state. Okay. Now I need a couple of facts of linear algebra, which go back to actually work done in mechanics. This is called Williamson's normal form in this literature, but I recognize this as a normal form of Birkhoff in mechanics long before, like more than a century ago. There's a paper in Annals of Mathematics by Birkhoff. Essentially, it's a statement that any harmonic oscillator, any oscillator in mechanics can be brought to its normal form. Okay. So if you have a positive matrix, if you have a positive real symmetric matrix, which is positive, I can pose this eigenvalue problem. Z is a vector, complex valued, and J is that matrix I defined, and I is square root of minus 1. You can pose this eigenvalue problem, and it's not difficult to show that the solutions are real and they come in equal and opposite pairs. If Z is an eigenvalue, Z star is also an if Z is an eigenvector, Z star is also an eigenvector with the opposite eigenvalue. So I will, to avoid the redundancy, I will choose the positive one, and I'll call that the symplectic. These are called symplectic eigenvalues of a matrix. Another way to think about it is that a symplectic eigenvalue of G is a positive eigenvalue of this matrix, minus Ij, just because J squared is minus 1. Okay. This theorem is that there is a canonical transformation, an element of the symplectic group, such that SG, S transpose is diagonal, and its diagonal eigenvalues are these eigenvalues, but each one appears twice. If you like, one is for momentum and the other is for position. So this is exactly what you would get if you take a positive function on a phase space, thought of it as a Hamiltonian of an oscillator, and you brought it to normal form. These gammas are the natural frequencies. So this is a familiar theorem, but in this context, it is called Williamson's normal form of a symmetric positive matrix. And there is this paper by actually people we know, Simon, Sudarshan, Mukunda, which is a nice paper, and they prove a kind of converse to this. Okay, the converse is that given a matrix which satisfies the stronger positive condition, there is a Gaussian state with that as the correlator. So what's a Gaussian state? It is what you would expect it to be. The expectation value of the exponential of a linear combination must be a Gaussian. So this basically says that all the correlations, all the higher order correlations are given by the correlation matrix through the Wick expansion. That is what a Gaussian. So if that is satisfied, you say the rho is a Gaussian state for this particular choice of observables C. They must satisfy canonical commutation relations. So that's what a Gaussian state is. And they give a proof of this, which something about co-adjoint orbits of the symplectic group and so on, which is, although I like those things, I think there's a simpler proof, and it's a proof you will recognize. It is simply that because this, let's consider, so this G can be brought to normal form by this theorem I just mentioned earlier. Now let us consider a harmonic oscillator, which is also in normal form. Now the question is, can I find constants H sub A, which are positive, such that this G0, which is diagonalized, is the correlation matrix of e to the minus h. So h is a quadratic function brought to normal form. You take its exponential, that's a state. In fact, it's a Gaussian state. This is actually a thermal state. Okay. So this thermal state of a harmonic oscillator is well known to be a Gaussian state. It is the Merlot formula of quantum mechanics. Okay, so now the only question is, given a G that satisfies that inequality, can I find H such that rho of Ca plus Cb over 2 is G0? Can you do that? That's a simple thing to work out. You know the spectrum of this operator. So, so this rho 0 is actually a diagonal matrix. So you can work this out because you know the spectrum of this to be odd numbers. And you can just compare this and you will see that this is true provided that gamma and h are related by this formula. Gamma is 1/2 the cotangent. Well, now you see why that inequality must be satisfied, because cotangent is always greater than 1. So these frequencies, gamma, must be greater than 1/2. That explains, if you like, that inequality. And conversely, whenever gamma is greater than 1/2, there is such an h. You want this h to be real and positive. Okay. So anytime I have a G satisfying that inequality, there is a state, a Gaussian state, which is actually the thermal state of some harmonic oscillator, for which this G is the correlation matrix. Yeah, so I'll assume that they're all unequal, but that's not necessary. If the gammas are unequal, the proof of that theorem is simpler. But if some of them are equal, it is still true. It is simply that the canonical transformation is not unique. We can do rotations. So that's the answer. So the proof is sometimes involved, but that's a technicality. I skipped the proof for that reason. Okay. So what's interesting is that essentially all the states I'll talk about are thermal states, although the actual field is in the ground state. The point is that you're only measuring just a couple of degrees of freedom of a system with a large number of degrees of freedom. So the effective density matrix on that subset is a thermal state of some harmonic oscillator. Okay, what that means, that depends on, yeah. So the temperature, see, what matters here is not the temperature by itself, but the temperature times these frequencies. And that is given by that formula, cotangent H. H is the product of inverse temperature and the frequency. So that's all that matters. So I am resisting the temptation to make connections to the Unruh effect and so on. I just want to stick to the theme of what I want to talk about. Yeah, but clearly there is some connection. Okay, so let me ask a question. What if this inequality is not satisfied? What if G is not greater than this half minus ij? What happens then? Well, it is still positive. It is possible that it's still positive. So suppose G is positive, but this is not true. That means that one of these eigenvalues of G is in this range, from 0 to 1/2. Well, in that case, I can no longer talk about an H. Okay. But I can still talk about a rho. I mean, I can still construct something like this. This H may be not in the required range, but you can still construct it. You can still construct a rho, and you can ask what is a spectrum. I can eliminate H from the story, and I can describe the spectrum of rho directly in terms of gamma. I just eliminate H from the story and just directly describe it in terms of gamma. And you will see that the spectrum of rho is given by this formula where nu runs over the integers, 0, 1, 2, and so on. And clearly, they're all positive as long as gamma is greater than 1/2. So the question is, what happens to the spectrum of this rho if this gamma is in the range, one of these gammas is in the range from 0 to 1/2. And if you look at that formula, you can see that some of the eigenvalues are negative. To be precise, all the odd eigenvalues are negative. Because if gamma is in the range from 0 to 1/2, this number here is negative, and a negative number raised to an odd number is negative. But the thing you're subtracting is smaller in magnitude, so it will remain negative. So roughly half the eigenvalues of this row are negative, which means the row is no longer a state. If gamma is greater than a half, it's a state. If rho is not greater than a half, it's not. It is what I call the proto-state. That is meant to be half as a joke, but yeah.
Some of the harmonic oscillator, it's a collection of harmonic oscillators. Some of them are negative H now.
Imaginary. Imaginary is not. That's why I don't want to talk about the harmonic oscillator anymore. I want to talk directly about the rho. Rho is still a sensible matrix. It is even positive. I'm sorry, it is diagonal in this basis, but some of its eigenvalues are negative. So it's not a state. The important thing is it is no longer a state. It's still a Hermitian matrix. It's still a Hermitian matrix. Okay, so the sum of the magnitudes of the negative eigenvalues is called the negativity of this proto-state. It measures how much this fails to be a state. By how much does it depart from being a state? That's what it is, okay? So this negativity is a simple geometric series, you can sum it, and it is just 1/2 minus gamma. So the thing to remember is that negativity is positive. Because the way they defined it, negativity is the sum of the absolute magnitudes of all the negative eigenvalues. Okay, so negativity is positive. Okay, I had to get through all this terminology to figure out what they're talking about. They also, so this means that if G is positive, remember all these things are invariant under canonical transformations. So if G is positive, we can construct a Gaussian proto-state, not a state, but a proto-state, whose negativity is the product over all gammas between 0 and 1/2 of this quantity. Okay. So far there's nothing about entanglement. This is just a statement about proto-states, if you like. But this comes in handy when you look at a criterion for entanglement due to Perez and Horodetzky. There are the 4 or 3 Horodetzkys. Okay, so now I get into waters that are quite deep, and I may say something wrong, but I hope I don't. So what is entanglement? Actually, I don't know. I have never seen a precise definition of what entanglement is. But I'll tell you what is not entanglement. Okay, when is something not entangled? So suppose I have a Hilbert space that is a direct product. And suppose you have a state that, however, cannot be split as the product of a state in H1 and a state in H2. I mean, operators in H1 and operators in H2. Then the following situation may happen. It is very possible in that situation that measurements by an observer who only has access to observables of this type and another observer who only has access to measurements of this type, operators of this type, are still correlated with each other, are still not independent of each other. And that is the phenomenon that I think is called entanglement. So in a situation when there is no entanglement is if rho is a direct product. That is, the state can be split as a direct product of 2 states. So what is a test for this? Okay, so here comes this really interesting paper of Perez from the 90s. And so he says, suppose I have 2 observers who cannot communicate with each other. They're space-like separated. Okay, how do you know that they're using the same square root of -1? Because square root of -1 has 2 square roots, I and minus I. We all have a convention about which one to choose, which one to call I and which one to call minus I. But how do you know 2 observers who cannot talk to each other? How do you know they're both using the same definition of I? I think that's sort of a facetious question. Perez is a guy with a funny sense of humor. So he's asking this question as a way to get you thinking about it. So suppose you have a state, rho, And I took all the states, all the quantities in H1, and I did a complex conjugation. So I take a state and I do a complex conjugation in H1, but not H2. It's as though you flipped the sign of I for one of the side, but not the other. Now, if you do that, rho will be transformed to some new operator rho prime. Okay. Now, if rho happens to be a direct product, then rho prime also has positive eigenvalues. Rho is a state, so it has positive eigenvalues. Rho prime, after a complex conjugation on one leg, will still be, because it's a direct product, another operator with positive eigenvalues. So suppose you found a rho which under this operation produces a rho prime, which is no longer a state. Suppose rho prime has negative eigenvalues, then you know that it cannot be a direct product. So there must be entanglement. This is the Perez criterion for entanglement. This is not a necessary condition, but it's a sufficient condition for entanglement. It tells you that if this phenomenon happens, you know the rho cannot be a direct product. So that's the idea. And then so you look at the negativity of, so the negativity is of rho is the sum over the negative eigenvalues of rho prime. You take rho, you do this partial complex conjugation, then you take the sum over its negative eigenvalues, you call that the negativity of rho. That is a measure of the entanglement of rho. However, I should warn you that, yeah.
What is implicit meaning definition of complex conjugation
Hmm.
and a complex use? It is an anti-linear.
Yeah, yeah.
Here, what is it?
Well, so in the examples that I will give, I'll talk about matrices that are explicitly written in some basis. And so the basis is given by that choice of canonical conjugate pairs. So the complex conjugation will involve reversing the sign of one of the pi's, one of the momenta. So I'll talk about.
Entries which are complex numbers.
The point is that momentum is represented by an anti-Hermitian, by a Hermitian but complex matrix, right? Momentum is represented in the Schrodinger representation, which is what I will use.
So entries are complex numbers.
Yeah. So I just flip them. That's right. So I'll use just that explicit definition. I don't know if there is interest in doing something more abstract.
So what does it mean as a criteria? Is it like an operation that one can
It is, yeah. It essentially it is something similar to time reversal, because in the way that I'll describe it, it is basically reversing the sign of momenta. So how exactly you implement it experimentally, I don't know, but it is something about reversing trajectories, the sign of trajectories. Yeah.
Taking partial transpose.
Partial transpose. Yes, that's right. Yeah.
Function is not a physical operator.
Yeah. Partial transpose.
Doing time reversal on one of them.
One of them. It's time reversal on one of them.
Entanglement detection can be done with physical operations also. Partial transposition is not a physical operator.
That's right. But maybe one observer can do that without involving the other.
But if it is a time reversal of the same Hamiltonian, then I think it is different. You want to kind of do the
Yeah. So how do you reverse the sign of momentum? I don't know how, but that's what it comes down to. You reverse the sign of momentum without changing position. You have two conjugate pairs. You reverse the sign of one of them. That's what the operation is.
Normally done by CPT of T.
T. This is T.
Here, again, partial transpose.
Yeah.
Again, I don't know what it means implicitly.
I don't know.
It's a complex Hilbert space.
Yeah.
And I wouldn't know what is transpose.
I mean, the naive answer I can give to that is that you essentially interchange in and out states. You know, like you reverse what is going in and what's going out. But beyond that, I don't know.
So what I mean, the moment you have a tensor product, you've already chosen the basis.
Yes.
Then I think it is clear what is the
Transpose is not clear because both
Partial
are
transpose. Partial transpose.
Both are complex Hilbert spaces.
Both are complex Hilbert spaces.
Unless
Yeah.
you work on reals,
Hmm.
then it is. Then it is.
Well, I mean, maybe I should think in terms of real vector spaces with complex
Then it is
structures.
negative operators.
With complex structures. Yeah.
Transpose or partial transpose, you can choose a basis with respect to which you have to do.
That's all I'm doing. Yeah. I don't have,
mostly,
yeah.
You know, the form of the partially transposed matrix will be different depending upon choice of your basis.
Basis.
The character
Yeah.
that it will have negative eigenvalues or all those things,
Uh,
that will not matter.
Yeah. So all I will do is to stick to a particular basis, and this basis is defined by your choice of U and V, basically. That's all I will do. There are probably interesting questions you can ask. Yeah.
Maybe this same question. Just
Yeah.
a different- I mean, time reversal as an operator is not local.
Yeah. But this has to be local. This thing that I'm talking about, only each observer has to do it separately. So this is why I'm trying to avoid the use of time reversal or things like that. I am going to. Yeah, that's not what this is.
He wants to be able to do it
It's independently. Yeah, one or the other. Perhaps I don't think. Yeah, I don't want to think in terms of symmetries and so on, because this may not be that. Yeah. So here's a. So there's a. But I should tell you something here, which is this negativity being zero does not mean there is no entanglement. It is it's a sufficient condition, but not a necessary condition, except in the case of two modes. So there's a proof by Simon that for the two-mode Gaussian state, negativity being zero does mean there's no entanglement. Okay, I'm not so familiar with this, so I know there is such a result. Okay. Okay, I won't use it because I will be looking for situations where this negativity is non-zero. That means there is entanglement. And in the two-mode case, that really is also a sufficient condition, necessary and sufficient. Okay, so what are two-mode Gaussian states? There are nice papers on this. In particular, this one I actually read. And I'll look at a couple of examples. So the first example I'll consider is one which does not have negativity. Okay, so this is a symmetric matrix, positive. In this range, if C1 and C2 are in this range, then this is a positive matrix, and its symplectic eigenvalues, in the way that I defined it, are easily calculated to be these quantities, symplectic eigenvalues. And we want these quantities to be greater than a half in order for this to be an allowed correlation matrix. Okay. Now let's do this partial complex conjugation. That amounts to multiplying C1 and reversing the signs of these two entries, because they correspond to the expectation value of pi1, pi2. This is the expectation value of pi1, pi2. And so you flip those two. Everything else remains the same. Now we ask, what are the eigenvalues, the symplectic eigenvalues of this matrix? We can calculate them too. So now what we want is to look for a situation where the symplectic eigenvalues of this matrix are all greater than a half, but at least one of the eigenvalues of this is less than a half. That cannot happen in this situation because it leads to a bunch of inequalities. I couldn't work it out by hand, but Mathematica can work it out and show that there's just no way that can happen. So in this particular case, at least the Perez-Horodetsky criterion does not detect any entanglement. And because of the result of Simon, there is therefore no entanglement. Okay. Let's go another example. Essentially, I want to interchange the roles of G and G prime. So suppose I choose this to be G prime. Again, C1 is less than A and C2 is less than A. And look at this situation. Now the eigenvalues are these. So these are the quantities that must be greater than a half. These are the symplectic eigenvalues. And if you reverse the sign, I get G prime to be this. Okay. Now it's a simple matter to ask Mathematica again to plot the range, whether there's a range where these are greater than a half, but one of these is less than a half. Now, if you think about it for a minute, you can see that the one that becomes less than a half cannot be this. So it has to be this one. Okay. And you can do this. And interestingly, there is such a range. So this little shape so this axis is A, this axis is C1, this axis is C2. Those are the three parameters. There is a range of values of A, C1, and C2 where this negativity is non-zero. So here is a situation where you might have an entanglement for a Gaussian with two modes. Okay. This is nothing I said so far is new. This is all in the literature, but I sort of pick out a couple of papers out of the thousands on entanglement where these results are worked out. Okay, but I can generalize it a little bit. I chose all the diagonal entries to be equal, but I can consider the case where these are the pi1 squared and pi2 squared have the same expectation value. Phi1 squared and phi2 squared have the same expectation value, and these inequalities are satisfied. And this, by the way, is not really a different example because this can be reduced to the previous one by a canonical transformation. But it is convenient to consider this example. Okay, so keep this in mind. Okay, now I come to the free scalar field. How am I doing on time? So this is the part of quantum mechanical entanglement theory that I will need. This, yeah. Okay, good. So I can go on. Okay, now let me consider a free master scalar field. To begin with, in 1 + 1 dimensions, and it's not the simplest case actually because of some technical issues which you will see in a minute. So let us define two fields. These are operator value. These are random distributions, so I must take some kind of a smooth function and average it out. So I define pi u and phi prime u. That is, I average phi prime, not phi. And they satisfy these commutation relations. And now we can ask, what are the entries of the correlation matrix among these two observables? Yeah.
1 + 1.
Yeah.
If you have free master scalar field,
Yeah.
the vacuum is not in the domain of the operator. You cannot define it. This is the theorem that
Yeah.
there are no goals
But
and nodes in matter.
yeah, but I avoid that by talking about phi prime.
So why are you saying field is not observable?
I want to avoid all that by talking about just phi prime. If you look at phi prime, I don't. Yeah. Let me ignore that. Let me say that I'll just work with this phi prime. So I will look at the observables, which are pi u and phi prime sub u, and u is a function that vanishes at infinity.
That's okay.
Yeah.
So you are eliminating phi itself.
Yeah.
Is observable by hand. That's it.
Yeah, only look at derivatives.
Ah.
That's what I'm doing. Yeah, by hand. Yeah, that's right. That just avoids some technical issues for me. Okay, now it's a simple matter of quantum mechanics. This basically the virial theorem of harmonic oscillators, that the kinetic and potential energies have equal expectation value in the ground state. And that tells you that pi squared and phi prime squared have same expectation value. And it's basically the matrix element of the frequency operator. So the frequency operator is defined here. You take u, you take its Fourier transform, multiply by mod p, and then transform it back. That's the frequency operator. So everything will be ultimately written in terms of this omega. And the tricky part is that this omega is not a bounded operator, so there will be some potential divergences. And so we have to work with that. Okay. So here I use some tricks of functional analysis. And these tricks of, did I do that? Or? Okay, all right. Yeah, so these tricks of functional analysis are there in all the functional analysis book, but there is this very nice review called The Hitchhiker's Guide to Fractional Sobolev Spaces, which gives all the tricks. This is basically Fourier transform, but used by a real expert of Fourier transform. And you find this formula. This formula for the frequency operator, which is written in terms of Fourier transforms and inverse Fourier transforms, can be written in an explicit way, directly in terms of u. So the naive formula will be something like, u of x plus y or x minus y divided by x minus y squared. But you have to do some subtractions. This subtracting a constant, this first term here is a constant you're subtracting. That constant subtraction is what you need to remove the ultraviolet divergence, so to speak. Okay. So that is what is the tricky part here. So you use that. Yeah, so it is this term here, which is u of y. So omega u acting on omega u evaluated at x is this integral. Naively, we would think of that first term as some sort of constant, meaning independent of x. But if I remove that from the story, this integral doesn't converge. You need that to make this integral converge. Okay, so that is the trick.
Looks a lot like the discrete second order.
It's a lot like that. Yeah, yeah. This looks like the discrete Laplacian. Yeah, and that's not a coincidence. That is what removes this. Okay, but I will need a sort of averaged out version of this. So this is the matrix element of the frequency operator between two functions of convex, smooth functions of convex support. So this is the matrix element of the frequency operator, and it has this nice formula. So here too, notice there's a subtraction, u of x minus u of y. Now, if u is a smooth function, you can see that this is actually a proper integral. There is no actual singularity here, because as x goes to y, the numerator also vanishes. And so this is actually a regular operator. This is a simple trick, but it really avoids all the infinities. So remember, the point is that a free scalar field is something we understand so well that it doesn't really have true ultraviolet divergences. If we just do the analysis properly, it can be done without any regularization. You don't need any regularization. This is not an improper integral. This is a proper integral. Okay, so now, so what do I mean by I'm going to now consider a two-mode Gaussian I can construct out of the scalar field. So I'm going to consider two regions, I1 and I2. I1 is an interval of length b. I2 is the same kind of interval, but on the other side of the origin. I2 is minus I1. So they're separated by a distance r. And this reflection symmetry is needed to simplify some things. Remember that when I talked about the two-mode Gaussian, the diagonal entries are pairwise equal to make the analysis simpler, and that will be achieved by this reflection symmetry.
Just show the first place where you have the frequency operator. Show it. The one before, there was a place where it showed up. Yeah, so this is, so the claim is that the frequency operator shows up when you compute this phi square or phi prime square
Expectation values.
expectation value, and this is essentially the expectation value in the vacuum.
Yes,
So,
yes, yes.
And you're regulating the ultraviolet.
Yeah, so I wouldn't say I'm regulating it. Regularization would mean I put some cutoff and took some limit. You don't need to do that. Basically, I'm doing a subtraction that removes the infinity. It is more like what we used to do. It's more like removing the 0-point energy by subtracting a constant from the Hamiltonian. It's something more similar to that. It's more similar. It's not true renormalization. It's more like a subtraction. And we know we can do that for free scalar fields. So that's what this is. By the way, these kind of things are called Rees kernels. If you ever want to look this up, Rees kernels are expectation values of the Laplace operator to a negative power. Sometimes even a complex number with negative real part. So this is called Rees kernels. So these are fairly, yeah.
At the moment, this is just a correlation function.
Yeah, that's all it is.
And you're expressing it in some way.
Yeah, that's all it is. And I use this particular form because then I don't have to worry about ultraviolet divergences. These are already convergent. That's all it is.
So this is literally the 0-point energy subtraction.
Essentially, that's what it comes down to. Yeah, but it is done in a more systematic way. That's right. Okay, so we now define 4 variables. Yeah.
0-point energy subtraction
Yeah.
might not affect your, the property of entanglement.
Apparently not, and that's what I'll come to. Yeah, apparently it doesn't. So let's define 4 variables, C1, C2, C3, which are basically the integral of pi. So this U1 is a function that is only non-zero in I1, and U2, V2 are only non-zero in I2. Okay, and then I consider 4 variables, which are C1 and C2 are the position and momentum variables on I1, and C3, C4 are the same things on I2. And it is not difficult to see that the correlation matrix has this form. The reflection symmetry is why this entry is equal to this. And this one is 0 because the pi versus phi expectation value is 0. So it has this form. So this is exactly the form I had before. And even the signs come out right. So this is the form I want. So A and B are these quantities. So A is the integral of u1 of x minus u of y squared and so on. And C, so here I've used this reflection symmetry so that u2 is replaced by u1 at minus y. So you can work this out. And so what we want is to consider the case where this has negativity. And remember, negativity is given by this formula. So now I ask the question, what is the choice of u1 and v1 which makes this negativity as big as possible? That's what we want. That's the same as minimizing this thing under the square root while keeping it real.
So somehow what negativity has accomplished is that it's somehow in this form of the integral that you have for the frequency operator, it effectively sort of regulates it and makes it, instead of if you're computing entanglement entropy, for instance, there will be a diagonal.
I am avoiding all those questions by formulating in this way. Yeah.
Negativity basically manages to avoid that.
No, it's not negativity. It is this choice of it is this formula for the expectation value that is avoiding the infinity. This is just a way to precisely formulate something we expect about. Yeah, that's right. This formula holds, in general. Yeah.
But the finiteness that you find there is a property
Of the field theory. Yeah.
So, but I'm saying that, but in entanglement entropy, if you compute,
I see. Okay.
you would actually find, because
I think.
expect that type.
Yeah. So I couldn't really penetrate that literature, so I took this other route.
Right. So that's why I'm saying that somehow the
Yeah.
negativity is doing something for you.
Possibly, yeah. What I heard from Natalie Clow is that people did not have a quantitative measure of entanglement. And then this idea of negativity provides that.
That's right. So, I mean, again, like if you have entanglement entropy, for instance, it is in some sense a measure for quantum mechanical systems. For field theory, it will be divergent.
Yeah.
So,
But in this situation, you can avoid those divergences. That is really the point. Although they avoid the divergence with with a lattice, they actually regularize things. But I'm saying you don't need that. You can do that in a completely.
I think that is related to the fact that it is specifically negative. It's a good measure for that.
Perhaps, yeah, that's possible. Yeah, because this is the only measure I know, by the way. I did not study.
Entropy will also be fine.
Yeah, it's possible. It's possible. And I would very much like to connect the two ideas. Yeah. Okay, so now I do a little scaling argument. You know that you can multiply u1 by a constant and v1 by the reciprocal constant without violating that constraint. I now consider the transformation of A, C, and so on. They transform in this way. So now the square root of A minus C1 times B minus C2 is actually the minimum of this sum under this variation. This is a scaling argument we see quite often. Therefore, maximizing negativity is the same as minimizing this sum subject to this constraint. This is a simple scaling argument. The advantage of that is that this is just a quadratic form. And so minimization of this essentially amounts to linear integral equations. So you get a pair of linear integral equations for u1 and v1, and they must satisfy these equations. And I want to emphasize that these are not singular integral equations. They look like, there is actually no singularity here. So here, for example, this integrand is actually regular at x equal to y. And here, because x and y are both positive, it never vanishes. So this is a ordinary, not a singular, this is a non-singular proper integral equations. And so, so I can reduce it to this as far as I got. What I want to prove is that the solution to these equations, when you put it back into the formula for negativity, gives you a quantity that depends on R and D, which decreases exponentially as a function of R over D. Okay. I'm not there yet because I thought that once I reduce to this equation, it will be easy to solve. Not so easy to solve. It turns out. I'll explain why another time. It has to do with the tricks of complex analysis. It turns out that solving these equations is very much a matter of doing highly degenerate perturbation theory. This quantity here is of order 1 over R. But this other operator, which is basically the frequency operator, and then there is a derivative operator here. Okay. Now, the point is that this lambda, if I ignore this term here, the eigenvalues of lambda are either plus or minus 1. You can see that. And now a small perturbation to the, so each of these eigenspaces for lambda are infinitely degenerate. And so essentially you're doing degenerate perturbation theory. Of course, you can make a living doing degenerate perturbation theory. There are systematic ways of doing it. I just haven't done it yet. Okay, so this is the original paper where this was done quite long ago, actually, 2009, by numerical work in 1+1 dimensions. Okay. Now I want to say a few things about dimension greater than 1. Conceptually, this case is a little bit simpler, although of course the details are complicated. So I can do exactly the same kind of thing, and this is the version in dimension greater than 1. Dimension 1 and dimension greater than 1 behave somewhat differently. And it has to do with the fact that the expectation value of pi is related to omega, and the expectation value of phi is related to omega inverse. You can just do dimensional analysis to see that. In quantum mechanics, the expectation value of the square of momentum is omega, and the expectation value of the square of position is omega inverse. Okay. Now, omega inverse is a bounded operator, even a compact operator. So this formula here has no ultraviolet divergences, no need for any subtractions or anything. This is perfectly fine integral. That's because if I expanded around some point x in y, there is a volume factor which exactly cancels this x minus y to the power n minus 1. So there is no singularity here. But there is a singularity here which is removed by that subtraction. So that is what this is. And these constants C plus and C minus you can get by some tricks of Fourier analysis. And the reason I cannot use this for n equal to 1 is that this constant C minus is singular at n equal to 1. So that's why I did it a little differently. Yeah, so for n greater than 1, there is no, for n greater than 1, there is no singularity. For n equal to 1, the problem is that this becomes a logarithm. And I want to avoid that by looking at phi prime. So that's why I treated that case separately. So I treat n equal to 1 and n greater than 1 differently. Okay, so again, the story is similar. I pick functions. So this time I choose these regions, I1 and I2, to be not intervals, but spheres of diameter d, separated by distance r. I again choose them to be canonically conjugate, which in this case means that, and so on. I do essentially the same thing. If I assume reflection symmetry, I can get the same kind of matrix. The A and B have similar integrals to before. C1 and C2 are given by these, and so on. So you can work this entire thing out. I think I actually get similar integral equations here. And these integral equations are equations in n variables. But now remember that I have two spheres which have an axis connecting their centers, and there's rotation invariance around that axis. So because of that, I can use cylindrical polar coordinates, and I can reduce this problem to an integral equation in two variables. The actual distance, the z and r, okay? And that's the best I can do. But when I started this project, so I am trying to solve those integral equations. It's a bit harder because integral equations in pairs of variables. Okay, but I want to make, if I have time, I want to make a couple of comments about conformal symmetry. So the thing that got me interested in this project is that usually correlation functions in conformal field theories are power laws. So where's this exponential that they're discovering coming from? That is the puzzle. I didn't solve that puzzle, but that's the puzzle I want to solve. Why is there an exponential? First of all, this does not violate scale invariance. It's because it is an exponential dependence in R over D. That's a scale invariant ratio. Indeed, you can verify directly that these formulas I have here for various expectation values are invariant under translations, rotations, and scaling. So I have essentially three quantities, and you can check translation and rotation and scale invariance for all of these. Now, translation, rotation, and scale invariance usually implies conformal invariance. So I assumed there was conformal invariance here, but there's a tricky point. In order to convert translation, rotation, and scale invariance into conformal invariance, you need one more piece, which is a discrete symmetry. The discrete symmetry is inversion. Replace x by 1 over x squared times x times some constant. If this is, so for any positive row, there is such an inversion. Now, if there is inversion symmetry for any row, then I get conformal invariance. That's because the conformal group can be built out of translations, rotations, scaling, and one inversion. The extra symmetries of the conformal transformations are really just in the conjugation of translations, ordinary translations by inversion. So this inversion. And this inversion is also a symmetry. There are three quantities, K, L, and M. It turns out that L and M are still invariant under inversion, but not this quantity K. Okay. So what has happened here is that the subtractions you did to remove the ultraviolet divergence preserve scale invariance, but not inversion symmetry. And that is what prevents you from using that. Now, this was a disappointment to me because, yeah, so I'll come to what it prevents me from doing. It basically kills conformal invariance. Yeah, I didn't, but I had an idea, which I'll explain now, which my idea originally was that if you have any boundary value problem with two spheres, there is, for example, the Laplace equation with two spheres is separable in bipolar coordinates. You know, these are things that I learned before I came to graduate school, and I always wanted to use this thing somewhere. I never got a chance to use it. I thought this is my chance. Bipolar coordinates you can use to separate the Laplace equation in any dimension. Okay. But in order to do that, when I looked into it, it turns out that the reason why bipolar coordinates can be separable is precisely this inversion symmetry. There is an inversion that interchanges the two spheres. And you need symmetry under that in order for the whole thing to work. I didn't realize that only when I did this. So I had these moments of great excitement and moments of great disappointment. And then I found this poster by Kanye West, who has changed his name, by the way. He's a rapper in the US. And he says, I hate being bipolar. It's awesome. So I conclude with that. Yeah, so I can take any questions you have at this moment. Okay, thank you.
So, but what do you mean by separability here? So, like,
Yeah.
general Laplace equation is generally separable in everything. What do you mean separable in what sense?
Yeah, so it has to be separable with these boundary conditions. So the Laplace equation is separable. In general, it's separable, but there's a finite number of choices of boundary conditions, which is listed in all these old books. And one of the, if you look at that list, for example, in Morse and Feshbach, I learned it from a book by a guy called Sokolnikov, is the book I did. But Morse and Feshbach has a, for this particular boundary condition of a pair of spheres. And the spheres don't have to be the same radius. Even then, it is separable. So this is something I know well from my childhood, so to speak, but I never had to use it because that's not the kind of physics we do anymore. But I thought this is my chance. Okay. And it all comes down to that inversion symmetry. So I call this an inversion anomaly. This is much like an anomaly. The interesting thing is that you don't have a scale anomaly, but you have this discrete anomaly under inversion. But it doesn't matter. I mean, that's only a technical issue. It is just a matter of, in the end, you can probably solve it numerically. It's a little tricky to solve it, but that's what I hope to do. I hope to solve it numerically. That's right, yeah. That's right. I mean, I can reduce it all to some integral equation. It will involve two variables, functions of two variables. You can use either spherical polar coordinates or cylindrical polar coordinates. Bipolar coordinate, I thought you would never ask. I can go on for, you don't want to know. The answer is you don't want to know. Huh? Okay, yeah. Well, bipolar coordinates are basically, if you have cylindrical polar coordinates, you can transform from there into bipolar coordinates. They are a coordinate. It's basically it's an orthogonal coordinate system, and the surfaces of constant value for the coordinates. In one case, they are spheres, which are orthogonal to each other. Okay, and this allows you to. So if you have this kind of boundary, this if you have a pair of spheres, you can reduce it to that. And the people who found these things useful in the old days were like, if you have a capacitor, if you have a pair of capacitors, which are both spheres separated by some distance, this allows you to calculate that capacity and the distribution of the charge on the surface. So these are old-fashioned potential theory calculations. Yeah.
Morrison-Fishbach acid, no?
Morrison-Fishbach acid, yes.
So, go to the last question. First question is, you said there are two questions I will give. First thing you said you are observing only one mode,
One each.
one each.
Yeah.
Then they cannot be localized.
Yeah, I don't know what you mean by that, because I have these
So,
modes.
there is no way to take a quantum field and suppose you want to create one creation operator.
Yeah.
You have to multiply it by the exponential, integrate over all space.
No, I can multiply it by a function that is zero outside of some region, in this case a sphere.
Then it's not one mode, it will create all the modes.
No, maybe in the if you think in terms of normal modes, yes. This and
Doesn't
that,
matter.
yeah,
It's a theorem
yeah, no.
that
You see,
Einstein causality will not be fulfilled.
what?
Einstein causality will not be fulfilled.
Yeah, that's probably. I think what you're saying amounts to the statement that there will be entanglement. I think that is what you're saying. No. Then what?
Statement is that there are no localized projectors in a quantum field theory. That's a general statement.
I don't understand this, and you have
You
to.
cannot write a projector in the Hilbert space of your right. Suppose you have an algebra.
Let me ask you a different way. What is wrong with the four observables that I wrote down?
I can say one comment.
Yeah.
I think he is basically, what he's calling a mode is basically an integral over a test function.
That's all it is.
Yeah, it's
Yeah.
not an actual pi or
Then it will not be possible. What I mean is the theorem I can tell, but I cannot tell
I
it integrates with your statement.
okay.
There are no localized projectors. Suppose you have an algebra of observables and the state on the algebra of observables.
Yes.
So by JNS construction in a Hilbert space, can I project it, apply a projection operator which is localized in some statement, some space-like region? No,
See,
doesn't exist.
I don't know what you mean by that, because the point here that I'm trying to make is that I can take a quantum field, average it over a function of compact support. I can take the quantum field, average it over a function of compact support, smooth function of compact support. No. A function of compact support is,
It will fulfill Einstein causality,
yeah.
but it will not be of one mode.
I think what you mean by a mode, yeah, okay. So this is just a question of what a mode is. What these quantum artists people call a mode, and I'm using the same language, is simply any pair of functions that satisfy the canonical commutation relations. That's all it is. Yeah.
I don't know how this works.
Yeah.
Usually the theorem says
Yeah.
if you take such operators
Yes.
and act on the vacuum,
Yeah.
you create a dense interface in the Hilbert space.
Okay.
That's another way of
Yeah. Okay. So now I know what you mean. Yeah. So these don't the observables I'm talking about do not create a dense set of operators in the Fock space of the scalar field. Absolutely not. And that is the whole point. Basically, this is picking a small subset of states of the whole scalar field. So now I see what you mean. So you have a scalar field, it has a Fock space, right? I'm not trying to create all the states in that Fock space using these four operators I have. Absolutely not, because this is a very small subset of the states of the complete Fock space. And that is why these things are possible. That is true.
It starts by some hard writes in his book.
Yeah,
I'm very surprised by the theorem.
Yeah, no, I understand what you mean. What you're saying is that you cannot create all the states of the scalar field using these observables. That is certainly true. Using these observables, you can create a small subset of the states of the whole scalar field. Yeah, that is
One
true.
more question.
Yeah, that is true.
You are working with an algebra fulfilled generated by phi dot and phi dot is a pi, and you had phi prime.
In the scale of in the 1 plus 1 dimensional
That is
case.
the
Yeah.
starting point.
Yeah.
Now, this is a new operation you can do. For example, I take the operator minus exponential I, some real constant times pi integrated.
Mm-hmm.
You have to translate phi by a constant, but not these things.
Yeah, but not by a constant, because the thing I'm multiplying pi with has to vanish at infinity.
Right? No.
So-
This is an operator.
Yeah.
Is acting on a given algebra observers.
Okay.
So what it does for the real scalar field is that it changes the representation.
Yeah,
By
okay.
creating a infinite cloud.
Yeah, yeah.
So that is inequivalent representation of the algebra.
Okay.
observers.
Yeah, that may all be true,
Okay.
but
Here I don't know what it does.
yeah. So here, because I am only looking at observables that depend on the derivative of phi,
So the algebra is completely. I am saying.
Yeah.
The algebra is in some.
it's insensitive.
Change.
Yeah. So
What is the representation?
yeah. So all I'm saying is that the translation of phi by a constant for a free massless scalar field is much like a gauge transformation. Yeah, like a gauge transformation. It doesn't affect any of the observables I'm talking about.
That's not true for a scalar field. It gives you an inequivalent representation.
Okay. Yeah, I know that you love those things, but I am. Yeah, that's fine. I don't. That doesn't matter to the things that I'm talking about. Yeah, whatever. Yeah. You see, the point I'm trying to make is that the two observables that I need, which are pi 1, pi 2, phi 1, and phi 2, the 2 degrees of freedom. I should have used the word degrees of freedom rather than modes. The 2 degrees of freedom that I'm talking about are not affected by any of those transformations.
That is my problem.
Oh,
So there is now a new automorphism acting on the algebra.
yeah.
What does it do to the representation?
I don't know. That may be interesting to ask, but I don't think it affects the particular thing that I was asking. But yeah, that's probably an interesting question. I don't know the answer though. Yeah, it is unchanged. It is invariant under that transformation. Yeah, but that might be an interesting question to ask. Yeah. I think.
Try to figure out these exponential decaying these negative.
Yeah, that is the question. Yeah, I don't know how well known this result is, but it caught my attention that it is decaying exponentially. And so the exponential decay is interesting for a conceptual reason, because a lot of things you would imagine in conformal field theories are power laws, but this thing is an exponential. But of course, there's no reason why you shouldn't have an exponential in a conformal field theory, because this doesn't violate scale invariance because of this depends on this ratio. But the other thing is the exponential decay actually makes it perhaps tricky to measure it experimentally because it is small. So if you want to actually put this into practice, you will need especially sensitive detectors, because even things that vary like a power law, like the Casimir effect, are already quite hard to see. But this is something like a Casimir effect because it's a property of the vacuum. And so perhaps the exponential decay makes it a bit hard to measure it, and that's another reason to be puzzled by it. Yeah. So I don't have any. I can see how it can happen, but I don't have a proof that it does happen. But I do believe their result. I mean, they have quite solid evidence that that's the case.